Hello everyone, Mrs. Belo here. In this video I'm going to be going through the evolution notes, starting here on slide 2 and ending here on slide 6. I'm going to be discussing Earth's early history, and we will also practice calculating or using radiometric dating as well as one of our math skills. So evolution, we're going to get to the heart of that later, but for now I want to just start with the history of Earth, and then we will get to the history of life on Earth. So let's start with talking about Earth's history. So one way to look back in time, so to speak, is to look at the layers of rock that can tell us a story in terms of any fossilized organisms that can be trapped in those layers of rock, which we also term strata. And we can also look at the composition of those layers of rock too, to also get an idea of what Earth's history was, thousands, millions, even billions of years ago. I have a video here that you can watch. It is under helpful videos. I'm not going to play it here, but I highly recommend going and watching this. It's very interesting. This is a video about the visual representation of Earth's history using a football field, and it's quite astounding from a human perspective, like how long Earth's history has been, and we've only just been here for like a small fraction of that history. So please go ahead and watch that video before continuing in the notes. Okay, so as discussed in that video, the age of the Earth was talked about. So Earth is about 4.5 billion years old. That's very, very old. And using, scientists have figured that out using something called radiometric dating of meteorites that were thought to have formed around the same time as Earth. And we'll be talking about radiometric dating and what that is and how it works in a little bit. Generally speaking, Earth was formed by gravitational accumulation of dust. So in space, particles will clump together, and eventually we get this giant molten rock that eventually cooled. And once that started to cool, we got water that formed, and that was the beginning of our oceans. And that is where all life began, was in the oceans. If you would like to learn a little bit more about Earth's age and exactly how that was calculated, we'll be talking about a little bit and how to do some general calculations. But there's an article here from National Geographic, and then also how carbon dating works, and then a little bit more of where did life come from, and that talks a little bit about Earth's history as well, and so does this video, more so the geological perspective on Earth's history. So all really good videos to watch. So radiometric dating. So we can determine the age of rocks or fossils by using something called radiometric dating. So this is a technique that uses the natural decay rate of an unstable isotope, and this is constant. So there are elements out there on the periodic table like carbon, uranium, nitrogen. Those are just a few that we're going to talk about that they can come in different forms. These are called isotopes. So for example, carbon on the periodic table, okay, there is normally carbon 14, and then we have carbon 13, and we can also have carbon 15. Now, it's still carbon, it's just that the difference between these is their mass because of the amount of neutrons that they have present in them, okay? Actually, I'm not going to talk about that. Carbon 12, excuse me, is the other one I want to talk about. So carbon-12, this is the most common one in the universe. This is stable carbon. This is pretty much what makes you up as a human being. But there are other forms of carbon that are heavier. They have extra 1 or 2 extra neutrons, and this actually makes them very unstable. These are what we call isotopes, and because they're unstable, they will decay, they will release radiation, okay? And when they decay, when they lose like neutrons and protons, they're going to become different elements, okay? And that rate at which it decays and changes into a different element that is more stable, so like carbon 13, for example, when it decays, it will decay into nitrogen 14, which is a different type of element. So over time, that carbon, like let's say the little red dots are the carbon 13, will decay and change into, imagine the little green dots, that is nitrogen 14. And nitrogen 14, this is a much more stable element. So when these radioactive isotopes decay, so that's like the original one, the parent one, the parent isotope, it will decay into a more stable, so like the nitrogen 14 element. We call that the daughter isotope. And the rate at which that happens is constant. So it's always the same. And you can look this up for various elements. They have very specific, what we call half-lives. So a half-life is how long does it take for half of that element to decay. And we can use that to do some calculations and figure out how old something can be. So here's a visual representation of that. So a little radioactive isotope here. And if we look at the graph here, over time you can see that the amount of that radioactive isotope is going down because it's decaying into something else. The little blue dots being that daughter isotope, the more stable element. And that happens at a constant rate, okay? So we'll have here, that would be like the first half-life, so that's half the amount of remaining. Here would be the second half-life, so that's half of a half, which would be 25%, so on and so forth. Now, again, you can't, this will just continue pretty much infinitely because you can't create or destroy matter according to the law of conservation. So let's go through 2 practice problems here. So I have a radioactive isotope, thorium-230, and its half-life is about 75,000 years. So that means that it would take, if you had a sample of thorium-230, it would take 75,000 years for just half of it to decay. So the question is, what percent of thorium remains in a fossil after 300,000 years, okay? Well, first thing I want to do is figure out, well, how many half-lives have passed? If I know what 1 half-life is, this is 1 half-life. I want to figure out how many half-lives have passed. So I'm going to take that number, the 300,000, and I'm going to divide that by 1 half-life so I can figure out how many half-lives have passed. So this is 4. So this means that 4 half-lives have passed. Well, now I can take that number and I can multiply it. I could multiply it by, I could multiply it by this and I would get the same answer again, which is this. So once you know the amount of half-lives, you can also figure out like how old something is as well, which we'll go through in the next problem. So it's asking for the percentage. So if 4 half-lives have passed, well, if I started with 100%, 1 half-life would be 50%, right? Because half of 100% is 50%. So that would be 1 half-life. If another half-life were to pass, that's half of 50%, so half of 50% would be 25%. If another half-life has passed, half of 25 is 12.5%. And then a fourth half-life, which is what I'm looking for, half of 12.5% would be 6.25%, which would be our answer. So we really want to figure out how many half-lives have passed. And this is one way to do it mathematically. Again, I took the total amount of time that had passed and I divided it by how long one half-life is to find how many half-lives have passed. And then I figured out percentage-wise, what would that be left over? So let's do another problem. So that thorium we were talking about, this is what it decays into, radium-226. So let's say we have 25 grams of the original parent and we have 75 of the daughter, okay? So the first thing is we have to figure out the total. So we have the 25 grams plus 175 grams. That would be the total amount that we have, because remember, both of those together would be making up the total amount, okay? Both the parent and the daughter of that sample. And we're trying to figure out how many half-lives has passed and how old is this sample. So let's, on the top, we're going to put the 25 grams because that's the amount that we have remaining. So 175 plus 25 is going to be 200. So 25 divided by 200 is going to be 0.125 times 100 would be 12.5%. So this is the percentage of the thorium-230 that I have remaining, right? This is how much is in the total of the sample. That's how much thorium-230 we have remaining. And then I just converted that into a percentage. Now, if I actually look up here, we already figured that out. That 12.5%, that means 3 half-lives have passed, okay? So if we have, so that's how that answers one of the questions, but then it's saying how old is the sample? Well, if 3 half-lives have passed and I know 1 half-life, according to that previous problem, is about 75,000 years, I can multiply that by 3. So this sample would be 225,000 years old, and this is how much of the thorium-230 we would have remaining. And those are just a few examples of radiometric dating. And then the homework is the radiometric dating worksheet. So I have a table here that actually shows the parent and the daughter. So in this case, we're talking about carbon-14. So that would be the parent isotope, and that's going to decay into nitrogen-14. Excuse me, I misspoke in the notes. So carbon-14 decays into nitrogen-14. And the daughter would be the nitrogen-14. So you could see that the parent is going down over time because it's decaying into the daughter. So that means that the percentage of the daughter would increase over time. And that's one of the first questions you're going to talk about here. Again, it's asking why. So think about the law of conservation. Okay, you can look that up if you need to. And then a couple practice problems here. So again, using that, you can use the graph to help you with some of the problems. I added a little bit more information here to help you with checking the measurements on the graph. Otherwise, you can use the notes that we just did to help you problem solve.